environment. And all the 5 talks will be in order. And a few things to mention. First, for all the attendees, if you have anything to post on social media or any references, feel free to always use the hashtag ISMAR21 for example, from Twitter. And also, there are individual questions for each individual paper. And during the talk, if you have any question, feel free to post there or post it in the Zoom chat as well. Such that I can help you redirect the question to the presenter. And also for YouTube viewers, you can always register and join our interactive session from Zoom with registering to ISMAR. And after all the talks, everyone, including the presenters and audience, can join the Gather Town with the link provided on Discord, such that we can have an interactive discussion and everything, and to have the audience meet with the presenters. Okay, so yeah, well, let's start with our exciting session. And the first one to present is Dr. Ryan McMahon from University of Central Florida. Dr. McMahon is an associate professor who directs the extended and training lab in University of Central Florida. And the first paper is the cognitive load and usability of target-based and steering-based travel techniques. So Ryan, feel free to take the stage. Okay.
Great, thank you. So I'm Dr. Ryan McMahon, and I'm presenting on behalf of my students. So just an introduction to our work. There's many consumer VR applications that use either target-based or steering-based travel techniques. So just to generalize, these target-based travel techniques involve the system automatically updating the user's virtual location to match a target virtual destination. Common example here is the teleport technique. Another example is for steering-based travel techniques. These involve the user continuously controlling the direction of travel. So an example here would be a joystick technique, which is commonly implemented. So our goal here was to investigate and compare the cognitive demands of using common target-based and steering-based travel techniques through 2 within subject studies. And we also conducted visual meta-analyses as well to compare our results to some prior results. So for our 2 studies, we used a dual task evaluation methodology. So a dual task paradigm basically involves performing a cognitive working memory task while concurrently performing a travel task. We replicated the same dual task methodology that we actually employed in an ISMAR paper that was presented last year. So in this methodology, the cognitive task is a verbal to-back working memory task. So the way that this task works is essentially there's a series of letter cues that are presented to the user one at a time. And whenever a letter cue pops up, if that letter cue matches the same cue as to back, then the user would press the trigger button on the controller. If the letter cue does not match the same one as to back, the user would choose not to press the button on the trigger, or should choose not to press the button on the trigger. So that was the cognitive task. And then for the travel task, we used a multi-directional horizontal travel task. So this is basically an adapted Fitts law task. So traditional Fitts law selection task that's basically placed horizontally, and columns are essentially used for the targets, and the user has to navigate to each column in the sequence that is indicated here in the figure. So for our first study, we want to investigate the target-based travel techniques. The first condition for this particular study was the teleport condition. Many of you are probably familiar with this technique as it's pretty popular. It's basically a point and instant teleport technique in which the user points to target destination as indicated in part A. And when they release the button to select that location, they are instantly teleported to the new destination, which can be seen here in part B of the figure. The second condition that we investigated for this first study was what we referred to as the motion condition. This was a point and walk motion technique. Very similar to the teleport, the user points at the target destination to indicate it. And when they release a button to select it, instead of being instantaneously moved to that location, they are instead continuously moved toward the destination at a walking speed of 1.44 meters per second. And finally, the third condition for this first study was the automatic condition, which was an automatic walk motion technique at which the system automatically moves the user towards the target destination at the walking speed of 1.44 meters per second once the user looks towards the next target. So essentially, if you recall back at the columns, if the next target column is within a 40-degree threshold of the center of the user's field of view, they would automatically be transitioned to that next target. So using our dual task methodology, we first investigated cognitive loads. We investigated both accuracy and F measure. We did find a significant main effect for F measure. So F measure is a harmonic mean. You can actually see here on the right-hand side how you calculate F measure. It's a popular metric for any type of binary classifier. And essentially for F measure, we found that the teleport and motion techniques required significantly more cognitive load than the automatic technique, which essentially resulted in a higher F measure score. So basically, the higher the F measure, the better the cognitive load condition is. So again, in short, the automatic technique was significantly better than the teleport and motion techniques in terms of cognitive load. Additionally, we also found a significant main effect on mean travel time per trial. So in other words, how long it takes to travel to each one of the targets. The motion technique was significantly slower than the automatic technique, which was significantly slower than the teleport technique. So as you can see here in the figure, in other words, the teleport technique was significantly the fastest. Then the automatic technique was also significantly faster than the motion technique. This makes sense as the teleport technique uses instantaneous transportation, while the other two use walking speeds. And it also makes sense that the automatic was faster than the motion because the automatic didn't require a selection confirmation as the motion technique did. In our second study, we investigated some common steering-based travel techniques. Specifically, we investigated three conditions, which are portrayed here in the figure. The first condition was the gaze-directed steering condition, which uses the forward vector of the head-mounted display to basically define what direction the user is steering in or continuously moving. In the second condition, we used a hand-directed steering condition, which can be seen in part B of the figure. And this uses the forward vector of the handheld controller. And then finally, we also did a torso-directed steering condition in which we would have the participants wear a chest strap with a Vive tracker, and we would use the forward vector of the tracker to determine the steering direction. All three of these were restricted to the ground plane to avoid any type of vertical travel. So, and this also makes the techniques more similar to most consumer VR applications. For this particular study, we did hypothesize that we may find that we might not find some statistical differences and that there actually might be some statistical equivalences. So for cognitive load F measure, we didn't find any statistical differences. So we actually conducted the TOAST procedure, which is the two one-sided test procedure. And this procedure indicated that the gaze and hand-directed steering techniques were statistically equivalent in terms of cognitive load F measure as indicated here in the figure. So again, gaze and hand-directed steering afforded essentially statistically equivalent cognitive load. In terms of mean travel time per trial, we also found that there were statistical equivalents between the gaze and hand-directed steering techniques, as they essentially afforded approximately the same travel time per trial. But we did find one statistical significant difference in the second study. We found a significant main effect of steering-based travel on total simulator sickness as measured by the simulator sickness questionnaire. Essentially here we found that the hand-directed steering technique induced significantly more total simulator sickness than the gaze-directed steering technique. And we believe that this is primarily due to the fact that the gaze-directed steering technique ensures that the optical flow is essentially parallel with your forward-looking direction, while with the hand-directed steering technique, optical flow could go across your forward viewing direction. Also in the paper, we conducted a series of visual meta-analyses based off of the visual inspection method presented by Dunlap and May, which allowed us to compare both our our current 2 studies, and also our results to our last paper, which was presented last year at ISMAR. Based off of these visual meta-analyses, we found that the automatic technique resulted in the highest cognitive load F measure and required significantly less cognitive load than the other target-based travel techniques, which would be the teleport technique and the motion technique, and all 3 of the walking techniques, which were presented in last year's ISMAR paper. In another visual meta-analysis, we found that the teleport technique resulted in significantly faster travel times than all of the other travel techniques, which makes sense because the travel is instantaneous as opposed to some type of continuous movement. We also found that the automatic technique resulted in significantly faster travel times than the 3 steering techniques, which are here in the middle, the motion target-based technique, and 2 of the walking-based techniques from last year, which were the walking in place and human joystick. And we also found that the walking in place and human joystick resulted in significantly slower travel times than all of these other travel techniques. And finally, the human joystick technique resulted in significantly more total simulator sickness than all other travel techniques. And the walking in place technique resulted in significantly more total simulator sickness than the gaze-directed and torso-directed steering techniques. So gaze-directed steering also likely induces less total simulator sickness than all the other travel techniques, except for the torso-directed technique. So based off of these results, we had a few recommendations. In terms of cognitive load considerations, we suggest considering the automatic technique when minimal cognitive load is a design requirement for travel, and the user does not necessarily need to control the travel. However, if the user does need to control the travel, but cognitive load is still important, we recommend either using one of the steering techniques or the teleport technique. In terms of travel performances, the teleport technique is likely significantly faster than all the other travel techniques, as it does not require time to transition to the destination. The walking in place and human joystick techniques require significantly more travel time than the others, so therefore those techniques should not be used. And then finally, in terms of simulator sickness, in applications in which simulator sickness needs to be kept to a minimum, we suggest not using the human joystick technique as it induces the most. And we also recommend that VR developers should provide a gaze-directed steering as an intermediate travel option between the novice-friendly teleport technique and the expert-friendly hand-directed steering technique. Interestingly, we have found that this was implemented in the popular game Half-Life Alyx, which uses blink or teleport, continuous, which is gaze-directed steering, continuous hand, which is hand-directed steering, and it also includes a shift technique, which is basically our motion technique. And all of this work was supported by the National Science Foundation. Thank you for your time.
Thank you, Ryan. It's a great talk. And while we're waiting for the audience to pose their questions, I have a few questions actually. Regarding the travel time, I wonder, do different methods provide or show different type of, for example, decision time, right? So if I'm trying to search my target using my arm versus using my gaze, more likely I need less alignment, for example, from the muscle than the gaze muscle, right? So did you compare that as well in addition to the travel time?
So we did look at things like missed terminations, which basically means that the user chose to travel to a destination shorter than the final destination. Interestingly, we found that basically the teleport technique resulted in more misses than the motion technique. So they both employed the same selection technique. However, the teleport would instantaneously get you there while the motion would continuously move you there. So essentially, we found that people were more careful with the motion technique than the teleport technique because they knew that it would take longer to get to that intermediate destination.
Okay. Yeah. Okay. Thanks. And yeah, we have one question from Discord from Hugo, who is asking, why would you recommend gaze-directed technique as an intermediate option instead of torso-directed technique? Do you have examples of applications when torso-directed should be a better option, in fact?
I don't have any examples where torso-directed would necessarily be better. Based off of this this figure right here that I'm showing, we do think had we had a larger subject pool, there actually might be a significant difference in terms of total simulator sickness between gaze and torso, because even though in general with torso, you will usually travel in the direction you're looking, it's not necessarily the case that you will do so. So essentially, gaze guarantees that you'll travel in the direction you're looking, which based off of prior ergonomics research and motion sickness research, that reduces simulator sickness. So that's why we recommend gaze as an intermediate technique as opposed to torso, because it will reduce simulator sickness compared to the other steering techniques.
Thank you. And we have one additional, probably last question from Gudrun Klinker, that would it make sense to include wayfinding tasks into this comparison of travel techniques?
Yes, absolutely. There's lots of different facets of travel. We were focused on the most simplified version of just getting from point A to point B for these cognitive load tests, because we were essentially wanting to measure the cognitive load of the basic function, regardless of wayfinding, because wayfinding adds a whole nother complexity. But I definitely agree that there's lots more studies that need to be conducted that also account for wayfinding in conjunction with cognitive load of just executing the techniques.
Thanks for the answer. So for the audience, you have additional follow-up or any questions, feel free to jump to the Gather Town to interact with Ryan after a session. Right. So now it's time to switch to our next talk. Hugo, would you like to? Okay, great. So our next talk is understanding modeling and simulating unintended positional drifting during repetitive steering navigation tasks in virtual reality. The presenter is Hugo Brument. He graduated from engineering school, INSA, RIN, in 2018, where he received his computer science degree. Now Hugo is a PhD student at the University of Ryan. His research interests include locomotion in virtual environment and also motion perception. And Hugo will give us this exciting talk. Take it.
Okay, thank you for the nice introduction. So I will talk here about the research paper called Understanding, Modeling, and Simulating Unintended Positional Drift During Repetitive Steering Navigation Tasks in Virtual Reality. So this work has been done in collaboration with Gerd Brüder from University of Central Florida, Maud Marshall from University of Rennes, Anne-Hélène Olivier, and Fernand Jarguet from Rennes as well. So to introduce our research work, I will start with one following questions. Who has ever experienced during user studies having some users reaching boundaries of the workspace while interacting with a VR software application? We all know that this will happen once when the user will hit the boundaries or the furniture or the physical workspace. And we all know that navigation is a fundamental task that enables users to explore virtual environments. While walking remains the most ecological approach to explore virtual environments, it requires a large enough tracking area that is not available on most VR setups. Some surveys show that most of the users had less than 3 per 3 meters workspace. So to encounter this problem, different solutions have been developed in the literature. For instance, we have some gesture-based techniques, such as walking in place, where we have to mimic some stepping place to explore the virtual environments on the left. You can also have some teleportation-based technique when the viewpoint would be automatically updated once you select a new target in the virtual environment. And you can also have some body segment-based steering techniques, in which you will define the future direction with one of your part of the body, such as the head or the torso or the hand. In this paper, we focus on the steering techniques. And even though we could imagine that these techniques do not necessarily require movements in the physical workspace, some research work showed that, for instance, with a walking in place, user may drift in the workspace while using locomotion techniques in VR. This phenomenon was introduced as an intended positional drift by Nielsen and al. And it was first noticed with walking in place techniques. As you can see in the video, while performing walking in place, the user might drift from its initial place in the workspace, and the repetition of movement and the discrepancies between the physical and virtual motion could induce some drift from the center of the workspace. So UPD can be problematic as it decreases user safety that could reach and hit the boundaries, and also decrease the sense of presence if you need to reset and replace the user at the center of the workspace. And also a very recent study showed that it can also affect task performance when people will perform the task slower for some techniques. Then our motivations for this research work was to investigate the UPD during steering navigation and to see that does it also exist while using the steering techniques, such as it was shown with walking in place. So to answer this question, we consider the following methodology. First, we collected some locomotion data that we analyzed to create and generate some UPD models that could be used to simulate, and then having with an iterative process, having some simulated locomotion data that we reuse to create new models. The objective of this methodology is to have a better understanding of this phenomenon, the UPD. So the first research question is about the analysis. Does UPD occur during a repetitive steering navigation task? That was the first question we wanted to answer. The second was regarding the model. Is it possible to quantify and model UPD for a given navigation task? For instance, finding some invariants or explanations of why users are doing this. And the last one is regarding the simulation. Can we assess UPD through simulation-based experiments like it's already done with redirected steering, redirected walking techniques, sorry. So to perform analysis of UPD, we got a data set from a previous experiment where users had to perform a repetitive slalom task using a torso-directed steering techniques. So the data set consists on 18 users with 648 slalom recorded. The data set contains the time for each frame, the head, shoulders, position, and orientation in both virtual and real environments. So before analyzing the UPD into more details, we did some pre-processing on the data. We consider the analysis both in real and virtual environments. We define the UPD as the physical displacement of the user in the real environment, as you can see on the bottom figure, where we computed the user's position in the workspace as the barycenters of the shoulders, as you can see. We also computed the user's amplitude that consists on the amount of users' rotation across time, as you can see on the top figure. A negative amplitude means that users were performing a left turn, and a positive, a right turn. We separated the virtual trajectories into virtual turns that are portion of the slalom between two inflection points. And last, we consider the UPD on both axes of user's workspace. The first one is the mediolateral axis, the ML1, that correspond to leftwards and rightwards UPD. And the second is the anteroposterior AP axis that correspond to forward and backwards drift. But in this presentation, we will only focus on the ML axis. And if you want more information regarding the AP axis analysis, you will find more data in the paper. Regarding the analysis of UPD, we computed the difference of users' position in the workspace between the beginning and the end of a virtual turn. You can see on the figure the density map of users' position after a left turn or a right turn. We can notice that the UPD occurred towards the direction of the turn on the ML axis, which is represented by a red arrow. Here you have the center of the workspace represented by the 0, 0 coordinates, and we can see that for a left turn, users will drift leftwards, and during a right turn, users will drift rightwards. This observation was statistically confirmed, and on average, users shifted around 20 centimeters after a turn. Further analysis regarding the analysis of UPD are available on the paper. We noticed with those analyses that the UPD is user-dependent, and we noticed some variability. Most of the users had the UPD towards the direction of the turn, as we presented on the previous slides. But we also noticed for 3 users some random UPD patterns, and also even one participant that didn't have any UPD at all, meaning that he was remaining static at the center of the workspace. Thus, we consider this variability when creating models. In the model, we decided to have 2 different approaches. The first one was a linear regression describing the relation between the UPD and users' amplitude, to have a relation explaining how the users may drift depending on how they are rotating in the real environment. As you can see, we see that the rotation, like when the amplitude is negative, we have a negative drift, so drift rightwards, and the same for the positive drift when we have amplitude when we have a positive drift. So you can also see that the last users, the 18 with the pink lines, has no drift, depending no matter what how it was rotating. The second model was based on Gaussian mixture models that are probabilistic model based on Gaussian distribution. We were able to fit some ellipse based on the data points we had between the drift and the amplitude of users. And we were able to compute this ellipse with the center and the covariance matrix for each user. If you want to have more details about how the values and the final results of the model, you can find more detail on the paper. Thanks to this model, we were able to simulate new data and in particular, reproduce the experiment we did with real users. So simulation-based operations are common to assess redirected working controllers. Then we suggested that we could follow the same methodology to simulate and assess our UPD models we created from our data. We created new navigation using the UPD model through simulations. The objective was to compare those simulated data with the user study data. On the video, you can see an example of the simulated tasks thanks to our simulation framework, in which we had two agents, one virtual represented in purple and one real agent represented in white, to simulate virtual and real users' movement. The purple agent is performing the virtual slalom, while the white agent is rotating and drifting as he was using steering techniques. So he's drifting in the workspace based on the UPD model we learned, and we simulated 18 users and reproduced the same protocol than in the previous experiment to generate new motion data. Thanks to this data, we were able to learn new models and to compute linear regression and new Gaussian mixture models, and we could compare those together. Regarding the results of the simulation, we performed the same analysis methodology to estimate UPD model from the simulated data, and we found no statistical comparison between the real data and the simulated data. So you can see that the GMM is for the Gaussian mixture model, the linear for linear model, and the real data that we got. This suggests that the use of simulation-based evaluations could be feasible and would allow the repetition of multiple simulations while modifying or updating the models. To sum up, in this paper, we presented for the first time a characterization of UPD during a repetitive navigation task using steering techniques. This provides additional insights about understanding the UPD, where first we had only information about walking in place. And the takeaway message from this study is that during curvilinear trajectories, such as in the slalom, users may drift towards the turn direction. The potential reason of UPD could be that quick whole body rotation can be difficult, and then when users are trying to rotate and perform the virtual slalom, they will shift without being conscious that they are drifting in the real workspace. Such results could be used in the designs of new navigation techniques, and in particular, we suggest that the use of gains could be used to influence users' movement and compensate the UPD. In future works, we want to assess other types of navigation tasks and techniques because we suggest that the UPD may be task dependent and therefore our models are not generalizable, but our whole methodology shows the pipeline to analyze and understand UPD for a given task. We also want to improve the simulation framework to release it to the VR research community. In addition, we want to test and use new metrics, other metrics to model UPD. We could consider the linear speed or the angular speed or the curvature of the trajectory. But in this example, we only focused on the amplitude. And last, other approach to model UPD should be considered, like we could use some reinforcement learning to learn on the fly the UPD models while users are navigating. Thank you for your attention, and I'm glad to answer to your questions now.
Thanks, Hugo, for the great presentation. Again, while others are preparing for their questions, either on Zoom or Discord, I may take a stage first, asking my questions. I'm very interested in knowing this phenomenon that everybody can inevitably work, right? So it's exciting discovery. But meanwhile, I'm interested to know what is the reason or thus the factor that affects the level of UPD. For example, is it if that's from, for example, lack of positional or depth queue in the environment, right? And then the person, if I mean, for example, if I stand in an empty background versus I'm staying in a very compact room, right? So they give me a lot of different depths and positional cues. Do you see any difference among this type of factors from the visual cue, right? So for example, during the motion, we may lack a visual cue, thus causing the UPD, right? Another reason could be because of the total muscular cue, right? So while you're walking, while you're jumping, you may not have you may lose your precise positional cue from the muscular motion, right? That could be another reason. In that case, the faster you walk, right? So the higher likelihood that you get a stronger UPD you will, right? Did you discover any difference among different cues, which is the reason behind?
Yeah, in the paper, we didn't describe the whole protocol that we did in this study, but we in this study we tested 3 different transfer functions. So the way that the speed was updated was different. So it means that we noticed that when we didn't find a lot of effect, but with the analysis, we noticed that sometimes when the motion is a bit reduced, it may tend to reduce the drift. So it's like the slower the navigation speed, the slower the UPD might be. But those are not confirmed with the analysis we had in the paper, but they are discussed. And the other factor is when we notice some effect is the curvature type. So the higher the curvature, the highest may be the drift, because it would be higher to perform the rotation. And so maybe there may be some interaction between the type of trajectory and the navigation speed we have. But we only tested this with only one data set, and that's why we need, and we suggest that the UPD is maybe task dependent and multi-factor dependent, and those are just we are just starting to investigate maybe more factors to have better understanding of UPD during navigation steering task.
Gotcha. Thank you. And it's very challenging to parameterize all these factors, I believe, to have a statistical model that describe it. So yeah, I personally had this experience as well. So there's like a fitness in Nintendo Switch, right? So in there are some like navigation tasks that basically you practice on the yoga mat, and sometimes I had this drifting as well. Right? Yeah. So for the audience, if you have follow-up questions on Hugo's presentation, feel free to post also on the Discord, right? So I think Hugo will also be there to check your questions, and we can interact that. And if you have post presentation type questions, you can also jump to the Gather Town after the session. Okay. And yeah, so far we have not received the updated question. Yeah, but we will interact on Discord, right?
Yeah, perfect. Thank you.
Thank you. So now let's switch to the next talk. It should be now. Okay, hi. So now our third talk is redirect walking in a static and dynamic scenes using visible polygons. The presenter is Niall Williams. Niall is a PhD student in the computer science engineering department in University of Maryland, College Park. Niall's research covers broadly in virtual reality and robotics. And feel free to take the stage now. And for the audience, feel free to post your questions on Zoom or Discord that we will discuss now after talk. Okay.
Thank you for the introduction. So, yep, I'm Niall. I'm a PhD student at the University of Maryland, and I'll be talking about redirected walking in static and dynamic scenes using visibility polygons. And this is work as part of my PhD under the supervision of Aniket Bera and Dinesh Minocha. So in VR locomotion, the user is located in a physical world and a virtual world at the same time. And usually these environments have different layouts and they have different sizes as well. And this leads to a fundamental problem in VR where the user may want to travel along some valid path in the virtual world, but it might correspond to some obstructed path in the physical world. And so one way to mitigate this problem is with redirected walking. Redirected walking is a technique that allows us to decouple the shapes of the user's physical path and their virtual path. And so the end result is that we're able to apply redirection to steer the user around in the physical world while they walk around and steer them away from objects without interfering with their virtual experience. In redirected walking, we have a user and they're located in some environment. We also have the user who wants to travel along some virtual path, and for this virtual path, they can be steered along a range of different physical paths. And if the user gets too close to an object in the physical environment, they have to stop walking and they're prompted to turn around so that they're facing away from whatever object they got too close to, and then they can resume walking again. And we call that a reset. And so a redirected walking controller is just an algorithm that's responsible for applying redirection such that it minimizes the number of times the user experiences a reset. And it turns out that this minimization problem is pretty hard because the controller has to be responsible for doing some sort of geometric reasoning about the shapes of the physical path and the virtual path and how those paths relate to the objects in the environments. And this is not such a simple task to do in real time. But it turns out that this whole idea of computing paths and their shapes relative to objects in an environment is a very well-studied problem in the field of motion planning. So, oh, it seems my PowerPoint has crashed. Okay, I'll restart it. I'll try and restart it quickly.
Yeah, you can restart it because.
Okay, am I good? Do we see?
Yeah, I can see your slides.
Okay, great. So yeah, motion planning. It's a great way to do geometric reasoning. And this is a subfield in robotics. And as the name maybe suggests, it's all about figuring out ways to get some agent, like a robot, from point A to point B in an environment and do that safely. And this is where the first contribution of our work starts, where we show how to use motion planning for redirected walking. So in motion planning, you have an environment and you have some agent in the environment, like a robot or a human in our case. And the configuration describes the agent's state in the environment. And for this work, the configuration would consist of the position in the environment, as well as the orientation in the environment. And we say that the obstacle space is the set of configurations that yields a collision with objects in the environment. And then we also say that the free space is the set of configurations that do not yield any collisions. So you can think of the free space as just the region in the environment that can be walked around or navigated in. And so given this, we can state the motion planning problem, which is if we're given some goal location and an initial location or configuration, the motion planning problem is to find a series of connected configurations in the free space that takes us from the initial configuration to the goal configuration. And if we apply this problem statement to the redirected walking setting, we now have a user who's located in a physical environment and a virtual environment at the same time, and they want to travel along some virtual path in the virtual environment. And this corresponds to some path in the physical environment, which may or may not intersect with objects in the physical world. And if there's an intersection with objects in the physical world, we want to just apply redirection such that we transform the path so that the new path after redirection, all configurations along that path are within the free space of the physical environment. And that's just a way of restating the redirection problem, but in terms of motion planning. And once we do this, we have a motion planning problem with some additional constraints. So first, we have the maximum redirection constraint. So for any virtual path that the user travels along, there's a limited set of physical paths that the user can be steered along. And this basically just depends on the user's perceptual system. We also have the path deviation constraint. So if the user wants to travel along a path that yields a collision, there's a range of different physical paths, and we usually want to steer the user along a physical path that deviates less or the least from their virtual path while still avoiding the collision, because this is usually a more comfortable experience for the user. And then finally, we have the information constraint. So depending on the system setup, we may or may not know everything about the environment or the paths. So we may not know, for example, the physical environment layout, or we might not know what the user's future path will be actually through the environment. And to give a quick recap of the differences between the traditional motion planning and the VR redirection motion planning. So in both settings, we have at least one agent, but in the traditional setting, we have one environment, whereas in the VR setting, we have two environments. In the traditional setting, there's full control over the agent because it's some robot that we're controlling ourselves. And in the redirected walking setting, we only have partial control over the agent because the agent is just a user who can, at the end of the day, do whatever they want, really. And we also, in the traditional setting, only consider constraints that are imposed by the robot mechanics, such as how the robot moves. But in the VR setting, the constraints are imposed by the human's perceptual system, which is particular to whichever user is using the system. And then in the traditional setting, we focus usually on efficient and safe paths, whereas in the VR setting, the focus is usually on comfortable and safe paths. And so for this work, we have the following assumptions about our redirection system. So we assume that we know the layouts of the physical and virtual worlds, and we also assume that we know the user's configuration in both environments. But we assume that we don't know the user's future path in the virtual world. And that gives us a little bit of a problem because the way I've been framing things so far has all been in terms of the user's path in the environment. And to get around this problem so that we can still make use of motion planning techniques without knowing the user's path, we use the notion of a visibility polygon. So what this is just if we're given a set of polygons or line segments in the plane, and we have some query point, which we indicate here in orange, the visibility polygon is just the set of points in the plane that are visible from the query point. So that's shown here in blue. And if we actually imagine the query point to be the user's position in the environment, the visibility polygon is actually a very compact and clean representation of the subset of the free space that's immediately available or visible to the user. So the visibility polygon gives a nice notion of local space around the user. And we can use this to identify collisions before they potentially happen. So consider this pair of environments. If the user wants to walk forward here, they can't do this because they'll walk into the object in front of them in the physical world. And it's difficult to know that this collision will happen unless we know exactly which path the user will travel along beforehand. And in this case, we actually don't know that. But we can get around this and identify this potential collision without actually knowing the path with the use of visibility polygons. So if we compute the visibility polygons for the physical and virtual worlds, like we see here on in the blue and the pink, we can imagine sort of overlaying the two of them on top of each other, which is what we see on the right here. And actually, in this case, if we drew the same path that the user walked before, we see that the collision happens when the user crosses the border of the physical visibility polygon, but remains inside the virtual visibility polygon. And so using this technique of superimposing the two polygons, we can actually identify collisions before they happen, or potential collisions without actually knowing the user's path. And so in this case, if the user turns a bit to their left, the path is now within both of the polygons, and so they're able to freely walk without any collisions. And this is the core of our second contribution, which is an algorithm for steering the user around based on visibility polygons. So here's a high-level overview of our algorithm with full details in our paper. So on every frame, while the user walks around, we compute a visibility polygon in the physical and the virtual worlds, and then we divide these polygons up into regions, which we call slices. And on every frame, we figure out, okay, what's the slice or the region that the user is currently walking towards in the virtual environment? And we just assume that that's the region that the user is looking at in the virtual world, which we show here in orange. So we just assume the user walks in the direction that they're looking for this work. And then the next step is to figure out which slice in the physical polygon is most similar to the virtual slice that's being considered. And the way we measure similarity in this work is with the area of the triangles. And so in this case, we find that this triangle has the most similar area. And then the final step is just to apply redirection to steer the user such that their heading is aligned with the angle bisector of the best matching slice. And the idea here is that we want to steer the user towards a region in the physical space that is most similar to the region that the user is walking towards in the virtual space. And so here's a quick demo of this in action with a visualization of the polygons, and the appropriate slices are highlighted. So we evaluated our algorithm in 4 pairs of environments, 3 of which were static scenes, and the 4th of which had 4 moving objects in the virtual environment. And we compared against some state-of-the-art controllers, which are steer to center, artificial potential fields, and alignment-based redirection controller. And we compared against these controllers because they've shown some pretty good results in the past. And more importantly, they have similar assumptions about the information available, similar to our algorithm. So it makes the comparisons more fair. And we tested all these algorithms on the same paths in all pairs of environments. And what we found was that our algorithm, the visibility polygon method, it significantly reduced the number of resets that users had. So it reduced the number of times the user got too close to objects, which suggests that the users would have a better time walking around in our environment or with our algorithm than when steered with the other algorithms. And so while we did get some good results or promising results, there are some limitations. So first is that we only tested a limited set of walking paths because we use simulation in order to collect a large amount of data to get some meaningful numbers. And also we used area as a metric for measuring the similarity between regions in the polygons, which is actually quite a crude metric. There's lots of work on similarity of polygons. And so you can probably get better results with a better metric. We also only tested a limited number of environments. And we also only considered the single user VR case. Multi-user VR will probably add lots of complicated problems, which we haven't considered. So in conclusion, we showed that redirected walking is very similar to motion planning. And there's lots of prior work on motion planning from decades of research. And so it's probably in our best interest to start looking at some of the techniques they've developed to see if it's helpful for us. And we also showed that the visibility polygon is very well suited for redirected walking because it captures local space very easily and very cleanly. And then finally, we showed that borrowing even basic ideas from motion planning can yield significantly better results for navigation. And we believe that there's lots of room for growth because we've barely scratched the surface with the ideas of motion planning that we use in this work. And we hope that researchers in redirected walking and navigation in general start to make use of ideas from motion planning. Thank you for your attention, and I'm happy to answer any questions.
Thank you, Niall, for a great presentation. So again, while we're waiting for the Discord and Zoom audience, I may start with my question. So since I did some redirected walking research, one quick question I have is about this algorithm that you search the closest polygon or triangle area. Right? So is it a constraint search? For example, if my closest red triangle here is very far from the current closest, right? So what if it's above the threshold of redirection? What do you do? Do you do the constraint?
Right. So what we do is when we're searching for the most similar triangle in the blue polygon, we constrain it to be any of the triangles that are within 90 degrees of the user's current heading direction. So we won't compare with triangles, for example, that are behind the user, right? We won't consider those because, like you said, the redirection threshold would require too much redirection that is not feasible. So we only consider triangles within the 90 degrees left or right of the direction that the user is looking.
Okay, thanks. Yeah, we have a lot of questions received from Discord and here. So maybe I can start with a question from Q&A here. So Keigo asked a question, asked two questions. First is about can the proposed method applied if the virtual and physical space are really highly different in terms of size, right? The second is, could you elaborate a bit more on the case where a physical slice that is most similar to the virtual slice is located behind the virtual agent? Would that have a 180 degree turn? That's similar to my question, right. I guess, given from the method.
Right. So I'll start with the second one. Yeah. So we don't actually have a case in the way it's written because we constrain our search of physical slices to be within the 90 degrees of the user's heading. We actually never consider the triangles or the slices that are behind the user. So that's that problem solved. And then if the environments have very big differences in their size, yes, it's true. So this method, like it'll still be able to run and your program won't crash or anything, but the results you get will probably not be very good because the whole idea is that we're trying to make the environments or the user's local surroundings more similar between the physical and virtual. But if at every location, the discrepancy between the two environments is too huge, yeah, that's a bit too much for our algorithm to handle. And things will still work, but you may not get great results.
So all is a relative concept regarding how much you can do that. Okay.
Exactly.
Yeah, we have one additional question from Bill Bernstein. He's asking, can you comment on the computational load of conducting the performance for both a human and robot agents for redirected walking in general?
Sure. So computing visibility polygons is O of n log n if you consider n to be the number of segments. So you could think, so that's just like a number of walls, basically. So computing a single visibility polygon is actually fairly feasible. It's fairly fast. But as you get more and more objects in your environments, that cost is definitely going to increase. But actually in practice, so if you imagine moving this sort of system onto like a commodity VR headset, usually you'll have data from something like a camera sensor, and that data will already be constrained to be within something near the user's field of view. So you can compute basically a subset of the visibility polygon from that camera data. And since the camera data automatically sort of culls out any of the objects like behind the user that we don't need to consider for navigation, the performance will probably actually get a little bit easier, or the computation time might increase because you only need to consider whatever is coming in from the camera data sensors in that case. But you'll probably have issues with things like dealing with VR headset. For example, if it's a self-contained VR system, the compute power may not be that strong. So we haven't tested that yet on any headsets in like live demos, but we think it's still going to be reasonable because there's been so many advances in like the computer vision space. So, and there's some prior work actually in VR on computing navigational or navigable space like floor planes from camera data on VR headsets. So we think it's still feasible, although it might be a little bit trickier.
Thanks for the answer. Just a side comment, from my understanding, the method is highly parallelizable, right? So probably it can be run on the GPU to search for each individual direction. You can do like sparse sampling on each direction. Is my understanding correct?
Yeah, that's right. We didn't do that in this work, but yeah, that's like a next extension if someone wanted to implement this and get it working in real time for sure in all situations. Yeah.
Yeah, that sounds more like in real time. Okay, thanks. Let's move to the next one. Thank you. So our next paper to be presented is using multi-level procuring to improve performance in path following tasks in virtual reality. The presenter is Zhenshuo Liu. Zhenshuo is a PhD student in the computer science department at Columbia University. His research focuses on user interface design, augmented and virtual reality. So look forward to your exciting talk, Zhenshuo. Take a stage.
Yeah, thanks, Professor, for the introduction. So this is work joined with Carmine Alabeccio and Barbara Trubisky and my advisor, Steve Feiner. So in order to explain pre-queuing that start from queuing, we use queuing to refer to providing information about the current step in real life. For example, we can use a sign here label to queue a person to go to the right place to sign. And on the right side is an AR maintenance system built by our lab. The color line connects the parts of a component to its destination so the user knows where it should be moved to. In contrast, pre-queuing means show information about future steps. In music notation, when the users plan one part of the score, they also foresee the pre-queues for what comes next. On the right side is again eagle flight. The current step is to fly to the purple diamond here on the top. And the purple path underneath pre-queues the user what needs to be done next. That is dive down. Several researchers have investigated the effect of pre-queuing in path following tasks. For example, Herson and Hornbeck conducted user study on pre-queuing in path following on a 2D monitor with mouse and touchpad. In their task, the user alternatively moves between the central target and the highlighted peripheral target. The user always returns to the center target, which is implicitly pre-queued. Vollmer et al. Investigated pre-queues in a projector-based AR. In their experiments, the user followed a path between a set of buttons. The current target and the next one were highlighted using a different styles. In both work, it's shown that a single level prequeuing helps improve users' performance. But how about multi-level prequeuing? There are several examples of multi-level prequeuing, such as the following rhythm games. In Beat Saber, the older upcoming box represents 3 targets for users to select with their controllers. And in Osu, each circle here is a 2D target for a user to manipulate with their mouse and keyboard. So, but notice here, in these games, the user focuses on time accuracy rather than speed. And the queue and the prequeues here contains both visual and audio components. Inspired by these examples, we asked the following questions. For tasks that require speed, can multi-level prequeuing bring additional benefits? And how does prequeuing style affect users' performance? So to investigate these questions, we designed user study. Due to COVID, we ran the study remotely. We built it in SteamVR so participants can use their own headsets. We chose a path-following task like the previous research since it captures most of the characteristics of many real-life tasks, such as flipping switches on a panel. In our test scene here, there are 14 spots folding on SY plan, and the green sphere represents the user's controller. The queue and the prequeues guide the user's controller through the destinations. The queue connected the controller and the first target, while the successfully prequeues point them to the upcoming destination, and the prequeues successfully get thinner, dimmer, and their terminators got smaller. So in the study, we asked the user to traverse this path as fast as possible without making a mistake. So here's how the study looks like. So here's an example of a queue only. So the queue points the user to the destination, and whenever the user reaches the destination, a new queue will be shown. And here's an example of one queue and one prequeue. In addition to the queue, the prequeue shows what needs to be reached next. And wherever the user finishes one, a new prequeue will be attached to the end, so the total number of queue and prequeue will be unchanged. Here is the example of one queue and 2 prequeues. So in addition to the queue, the user is able to see the next 2 steps. Our formal study is designed to compare different visualization styles and determine the best number of prequeues for each style. Here are the visualization styles we tested. Informed by the pilot studies, we picked them because of the kind of information they provide. So here I'm going to introduce the information each of them provides. The first visualization is arrow line. It provides user with the path and place information. The line connecting the destinations will providing the user with the path information. And the arrowhead, it points to the destination, so it provides the user with the place information. And the second one is arrow. So it is a variation of arrow line, but it does not have line. So here, still, it provides the place information since the arrowhead points to the direction, point to the destination. But for the path information, it only provides partial path information, the direction information, since the arrowhead is oriented. The third visualization, circle line, is different from the arrow line in its terminator. So it still provides the user with path information, but for the it ends at the destination, so it highlights more on the place information. And the fourth one is circle only. So it does not provide path information, and it only provides place information. And the last one is line only. since it connected the destinations, so it provides user with path information. It also provides partial place information since it ends at the right destination. So here is our study design. We have 25 conditions, 5 styles we just introduced, and 5 number of precues 0 to 4. We picked them because in our pilot study, we figured out people are not able to use more than 4 precues. And for each block, for each condition, we have a block, and the order of conditions is counterbalanced. And in each block, we have 3 42 segments path per block. And the first path is a practice one, so user can get familiar with the new visualization. And the second and the third ones are timed. So here are our hypotheses. So first, for each visualization style, the user will perform better when 1 precue is provided than no precue is provided. This is in part to confirm that for the task we pick, the result will be consistent with the previous research on single precue. And H2, when the number of precues is fixed, the user will perform better with lines used in the visualization style than when lines are not used in a visualization. And H3, user will be able to make use of more precues for visual styles with lines than style without lines. We chose H2 and H3 because we believe the path information is crucial in the task. So here's our results. The x-axis here is number of precues, 0, 1, 2, 3, 4. And the y-axis is the time for each segment the user spent. Each line here shows results of 1 visualization style. And in our paper, the results are analyzed using the linear mixed model and pairwise comparisons. The overall trend here is that people's performance improves with help of 1 precue, but when too many precues are provided, they perform worse. So to validate the hypothesis, H1, let's look at this part. For each of the style, the user perform better with the help of 1 precue than no precue. So H1 is supported. Second, we want to compare the visualization with lines and without lines. So the top 2 are results for visualization without lines, and the bottom 3 are the visualization with lines. Note that here, what short time is better. So in for 1 to 4 precues, people do better for visualization with lines. However, there's an exception here. For no precue, only Q is provided, people perform the best with only with circle style. So this hypothesis is partially supported. And H3, the best number of precues, people are able to use 2 to 3 precues for visualizations with lines, but only able to use 1 for visualization without lines. So H3 is also supported. So we also analyze the error people make. So sometimes tracking issue happen. It can be seen from the discontinuity in the path, user controls path. Sometimes people go to wrong target because they just misrecognize targets. Sometimes people will go to right targets but fail to hit it. So this we call missed targets. Sometimes our issues happen, like maybe they got distracted in the environment, or sometimes it's just a mixture of the first 3 errors. So here are 2 from us. First, people tend to make more wrong targets in arrow and circle line. These are the visualization without lines. And second, for missed targets, these seems to be negatively related to the speed. Note that we ask them to finish that as fast as possible, but if the constraint change, the circle might not perform best. So the summary here is that people are multiple precues can decrease the completion time, and style with lines are better than no lines. And people are able to use 2 to 3 precues for style with lines, but only able to use 1 for visualization without lines. So, but however, please remember that our work has some the following limitations. First, the segments are relatively large and discrete. So when the path is fine-tuned and curved, it might be different. And our test is 2 DOF only, translational only. So when more DOF is content, the result might be different. So future work prior to the pandemic, originally we planned to do AR and rotate, and the test includes rotation. And our part is that it's possible to use Procure by manual task and parallel task. And that's how about for collaborative tasks in which multiple users are involved. So here's my presentation, and we would like to thank NSF for funding, and thanks our colleagues and the study participants. And we are recruiting, so come to see us in the Petrie lab session. Thanks, everyone.
Thanks, Junshou, for the exciting talk. And yeah, so I will start with the audience question from Discord. So now I ask a question, do you think there are types of navigation tasks where, for example, the pre-queuing can make the navigation performance harder, right? For example, where tasks the user have very high cognitive load to focus, and then would this pre-queuing distract their efforts to process that such that it can affect their final performance?
Yeah, I think the answer definitely will be yes, because in fact, the number of queues depends on what kind of task it is. So this one is like a simple task, so people can make more use of more queues. But in our other studies we conducted, like in the case rotation is like is included, people can only use less queue. And for like more complicated task like navigation, it's possible that people can only use 1 or even 0 queue. But yes, I agree that that might be related to the cognitive load.
All right, thank you. And we have one more question from Joseph Gabard. He's asking, do you consider different row head sizes? For example, through pilot testing, could a row head size impact the result?
Yeah, in fact, this is the changes we made in the pilot study. Yes, so that will make a difference. So originally we use visualization. Let me switch to my use slides here. Yeah, so in fact, in our pilot study, we have a different visualization here. So the error head is smaller. So we figure out that in this case, several participants told us they are not able to like differentiate the Q and PQs. So that's a reason. So it will to like address issue, we made the error head larger and also change its size. So definitely the error head size will affect the user performance, and the difference in the error head size for Q and PQ will also have an impact.
Thanks. Yeah, thank you. And yeah, while we're switching, I have like a very quick last question from myself is, from this observation, all the experiments are doing the pre-Q in your peripheral vision, most likely, right? So, and where you have like lower sensitivity to process information. What if the pre-Q, this pretty much related to Niall's question, what if your pre-Q occurs actually in foveal vision that may affect your performance in processing the majority of the content in your vision?
Okay, yeah, so I think in fact, well, I have a pilot study on this. So yes, that's also related to the vision, like which region it is in your vision. So if all of the targets, like if I reduce the radius, so they all like fall in my fovea region, then in fact, for all visualization style, I can use maybe 2, 3, or even more. But if I make the radius really large, so they are all fall, some of them falls out of my field of view, then for a lot of visualization, they can only use 1. So yes, that's also related to the peripheral vision.
Thank you, thank you. So now it's time to move to our last talk. Thank you, Junshou, for the exciting answer. So our last talk is from Alec Moore. The paper is personal identifiability of user tracking data during VR training. So Alec is a PhD candidate at the University of Central Florida. His research interests include VR training and also machine learning. So look forward to your talk, Alec.
Thank you for the introduction. Hi, everyone. My name is Alec Moore, and I'm excited to share our paper with you, Identifiability and Obfuscation from user tracking data from VR training sessions. So to get started, identifiability, there's been recent work that has shown that readily available tracking data, that is the data that tells the system where your head-mounted display and controllers are in immersive environments, can be used to uniquely identify individuals with up to 95% accuracy in a passive way. And so we wanted to see how identifiability is affected by a few different conditions. Namely, we wanted to look at how identifiable people are in interactive training tasks, how much identifiability is reduced when trying to identify participants across VR sessions. And finally, if there's a way that we can represent this data that's still useful while reducing the overall identifiability. That is, if there's hope for a way to represent data that's still useful to the system while preserving the privacy of the user. So to conduct this study, we made use of an existing robotic operating room training application. We ran a 2-session user study with 60 participants, 11 of whom were female. The average age was 22.6 years, and all of them had no prior robotic operating room experience, as one might expect. During the training session, the application trained users on how to troubleshoot a fault that the robot experiences, and then 1 week later, participants returned to attempt the troubleshooting procedure again. I would like to note that our data was collected before the pandemic through a procedure approved by the University IRB. So in the course of both the training and evaluation sessions, our system collected 18 values of data for every 90 Hertz frame presented to the participant. This data consisted of 6 degree of freedom values for each controller, as well as the head-mounted display, so the XYZ and the roll, pitch, and yaw. And so those values times 3 devices is 18 total values for every 90 Hertz frame. We then aggregated the frame level data into 1 second descriptive feature vectors consisting of the minimum, median, max, mean, and standard deviation. And because we have 5 aggregate functions on 18 values, that gives us a 90 valued feature vector for each second, or a vector in 90 dimensional space. We then also subdivided the total session into 10 even subsessions that we used for our analyses. So I'll quickly describe the models that we made use of. We used k-nearest neighbors, which treats all training vectors as points in high dimensional space, in our case, 90 dimensions. And when asked to predict the category of a new vector, it finds the k-nearest training vectors, usually by Euclidean distance, and it predicts whichever category occurs most frequently among those neighbors. Note that for KNN, we do normalize these vectors to a mean of 0 and standard deviation of 1. That prevents the scale of the input along different axes from affecting the prediction. Now, while KNN simply involves embedding the training vectors and their labels into a high dimensional space, random forest and gradient boosting machines are trained by building ensembles of decision trees that try to map vectors to labels. But both random forest and gradient boosting machines were implemented using scikit-learn defaults. So after being trained, all 3 of these classifiers attempt to solve our multi-class classification problem, which is to say they take a single feature vector, our 1 second descriptive feature vector, as input, and it returns a prediction as to which participant generated that feature vector. So our methodology for training and testing these models involved these 2 procedures. So for our within session predictions, we used a random subset of 9 of the 10 subsessions for training, and we withheld the remaining 1 for testing. And we're presenting the average results of 20 Monte Carlo shufflings. And then for between sessions, we trained on 1 entire session for a participant and then used the models to identify 1 of the 10 subsessions for the other session. And we show the average results of those identifications. And for both, while the classifiers provided a prediction for each feature vector, that is to say 1 prediction per second, we used the plurality of these predictions at the subsession level and said that each classifier ultimately identified the most commonly predicted identity for that subsession. So what did we find? Well, we found that for our scenario, gradient boosting machines performed the best with an average accuracy of 90.83%. Our GBM accuracy was substantially higher than expected, given recent work by Miller et al., which averaged 68.2%. But this is most likely due to our much smaller sample size. We had 60 participants and their study had 511. So that increases the probability of correct identifications. We also had a larger number of estimators in our GBM. We had 100 rather than 10, and that was made possible by our smaller sample size. We did notice, though, that our KNN and RF classifiers performed notably worse than those of Miller et al. And we believe that these results indicate that identifiability of users depends on the type of environment presented, including the level of interactivity and the amount of movement involved. So looking at identification accuracy between sessions, we see substantial decreases in identification accuracy on the models trained on one session and evaluated on another. We believe that there are many factors contributing to this, including differences in the fit of the HMD and the clothes the user may be wearing. Furthermore, there's also the fact that one scenario is attempting to teach users and the other is evaluating their knowledge, and that participants by definition have gone through the procedure once already by the time they begin the retention session. But ultimately, I'd like to point out that random forest reduced to 47% of its original accuracy, a decrease from 89.33 to 42.33. So finally, one approach that we know has been useful for predicting user learning and retention outcomes has been re-representing the data as velocity rather than position. So to keep our approaches comparable, we replaced the position and orientation data in each frame with the velocity and angular velocity, and then we computed the same per second feature vector as before. We then trained the models the same way that we did before, and we reran our approaches, and we evaluated the within session identification accuracy and the between session identification accuracy. And so our results show that our models had a much more difficult time now, uniquely identifying participants when their motion data was encoded as velocity instead of positions. Interestingly, the k-nearest neighbors approach appeared to be the least impacted by this re-representation, reducing to 43% of its original accuracy from 80.42 here to 35.17 here. So it also performed the best of our within learning session results. So when looking at predicting between sessions, we find that identification rates are now really low, but they're still better than we would expect from random chance. If you recall, we had 60 participants, so we would expect roughly a 1.6% accuracy just for guessing. So the fact that it's still performing better than that is surprising, a little impressive. So our conclusions, we wondered how identifiability of users changes with an interactive training task, and we found that it appears to be more difficult, but the models still perform much better than random chance. We also examined how identifiability is reduced across sessions, and we found a decrease in accuracy, again, indicating that it's harder but not implausible to identify users in different sessions. And we finally looked at how changing the data was represented by using a format that's seen use before for knowledge and predicting knowledge and retention outcomes. And we found this to yield the lowest identification accuracy that we saw. The model still performed much better than random chance though, but maybe eventually we can find a way to encode motion data that can still be useful to systems while preserving the privacy of users. So briefly, some limitations of this work. We didn't do cross-validation to determine optimal hyperparameters. If one were to do this, you would expect to see improved identification accuracy for the three models. We also only examined k-nearest neighbors, random forest, and gradient boost machines, which they don't really exploit the temporal nature of the data. And so something like a long short-term neural network might do a better job with this problem. And as mentioned before, there were several factors at play with examining identification between sessions. Our system trained users in the first session and evaluated them in the second, which means that while the actions that the user had to do remained constant, the triggering of prompts was different. And presumably the participants would know what comes next and could begin movement towards a given subtask ahead of time in the retention session. And finally, we didn't really control for clothing, including specifically shoes, which may have affected users' mobility to a substantial degree. So I'd like to thank you for your time, and I should be available for questions after this presentation. Thanks.
Thanks for a great talk, Alec. So I'll forward the question from the audience, starting from the Zoomers. Steve, okay. Steve, final question is, have you tried to determine whether a user that was actively trying to obfuscate their own motion, for example, doing some like a mix type of intentional motion, would be successful at concealing the identity, or at least making the method, the determination harder. And whether they could do that while also succeeding at the tasks where they were performing.
It's a very interesting question, actually. That's definitely something that I would like to investigate soon. Certainly, it would be kind of interesting to try to keep in mind that you're trying to trick a model into thinking that you're not yourself or that you're someone else specifically, and that and trying to do that while also succeeding at your tasks could be pretty difficult to keep in mind. But that's a very interesting thought. Thank you, Steve.
And I actually have a follow-up question related to Steve's. So the thing is, there are different type of modality. In this experiment, you did pretty much like a positional encoding and versus velocity that could reduce the performance. But there are some, and also these are essential metric to the performance, right? So if you try to reduce the identifiability, that may also affect their performance as a metric. But meanwhile, there are some other models, for example, like gaze, right? So in gaze, it's inevitable, I guess, to make up the gaze motion because it's rather passive rather than active muscular motion. How do you compare different models as the potential metrics to identify people while also keeping the performance alive?
So I think I'm sorry, could you rephrase the question a little bit?
So my question is, there are different metrics, right? So this is a position as a metric, right? So that can reflect your performance, but also your identifiability. There are other metrics, for example, if you use the user's gaze, where the person is looking at, right? So that may unlikely to have the user to try to make up their own motion because that's rather passive, right? So would that increase your potential, increase your identifiability while also maintaining the performance in general?
Right. I think what I know from biometrics is that things like saccades they would be pretty hard to control, and so if you were incorporating gaze data, you would probably have a harder time faking your motions to try to hide your identity. I know that there's been some work into trying to obfuscate gaze data in order to preserve the privacy of users as well. And certainly, I know that a lot of that work has been into kind of applying an intermediary layer that basically adds some additional noise to your view. In this case, we primarily looked at velocity just because we know that at best, you could just guess someone's height and their physiology and try to guess where their position would be. But you can't actually know that for certain if you're given just the velocity data.
Okay, yeah. But it's interesting to know, for example, velocity is a first order gradient, and then it can just trick the neural network for identifiability. And also we have an additional question from Louis. He's asking, do you think that using positional data to cluster group behaviors rather than individual identification could be a better way to increase the between session accuracy?
I would say probably. I know that when you're talking about doing larger segmentations of populations, it's a lot easier to identify people as being parts of those segments. That's why the Google cohort advertising setup was under some scrutiny earlier this year, because really, if you can segment your population, sometimes you can learn a lot of things about them that they might not necessarily want you to know, even if it's not to the level of detail as their actual identity. So I agree that you would definitely expect to see some higher accuracy in terms of clustering group behaviors instead of doing individual identification.
Yeah, thanks for the answer. And do we have any additional? Yeah, I don't see a question from the Discord, but feel free to chat with Alec in the chat as well. So thanks, Alec, and thanks all the authors to present their great work. And for the audience and also the authors, do remember to attend our individual interactive Q&A in our track B room in the Gathertown, such that you can have questions being asked, you can interact with the authors, and also the name, you can easily find a room follow Lucilla Damaco. Sorry, I'm bad at Italian, but there's a Lucilla room in the Gather town, and you will be teleported there. If you have any questions, Vito is also in the Zoom room. Vito can send you some links or answer the ways that how you should access the Gather town interaction. And all the papers will be ordered and noted with the order paper 1, 2, 3, 4, 5 in our session. And yeah, look forward to the interaction in the Gather room. So everybody, if you have time, feel free to join there. And that is the end of our session. Thank you for attending all the talks, and look forward to meet you there. Okay. Thank you.